All right, good. So it's a great pleasure today. We have our colleague from nearby, Olalla Castro-Alvaredo. So she did her PhD studies in Spain, then she has done postdocs in Germany and France, and for a while now she has been at City University in London. Um, she's interested in quantum field theories and quantum integral models, and some non-equilibrium aspects of these things, and in particular entanglement in these theories. And I think that's what she's going to tell us about today. So Lai, please go ahead.
Okay, thank you. So at any time, if you don't hear me properly, just let me know. This is my first virtual seminar so far, so I hope it will be good. Thanks a lot for inviting me. It's very nice to be here today, or to talk to you today from home. So I'm going to be talking about entanglement dynamics in quantum integrable models. As you have just heard, this is my main area of research, quantum integrability, in particular quantum field theories, integrable quantum field theories. So in the past 15 years or so, I have been interested in entanglement aspects of these theories, and more recently on out of equilibrium features of this entanglement. So if you hear my talk and you find it interesting, you might want to know more of the details, and you can find those. Oh, sorry, I was trying to. You can find those in these two papers that you can see here. So this is the result of some work I did over the past 2 years with these collaborators, Mate, István, and Jacopo. István used to be my postdoc at City, and he's now in Nordita in Stockholm. So we wrote these two papers. When I was invited to give this seminar, there was a particular interest expressed on the results of the last one, where we find oscillations of entanglement. But in a sense, both papers, or the second paper is a continuation of what we started in the first. So in this talk, I'm going to tell you a little bit about what we were trying to do in the two papers and present the main results of the two of them. So I talked about entanglement dynamics, so I guess I should start from the beginning and say what we mean by that. I think many of you would already be familiar, but the idea is that you want to look at the time evolution of some measure of entanglement after a quantum quench, so in and out of equilibrium situation. So you want to look at how that depends on time after the quench, if the quench is at time 0. Now, there are different quantities you could look at, but in one-dimensional quantum systems, a particularly interesting one, even in high dimensions, in fact, is entanglement entropy, so the von Neumann entropy. So imagine I'm talking about that for a moment. So let me call that S of t. Now, for that quantity in 1D, there is quite a lot that is understood out of equilibrium. And there is one result that is by now, I think, quite famous, which is this idea of Calabrese and Cardy, this result of Calabrese and Cardy, that says the following, that if you have a 1D system and you have this system divided into two regions, complementary regions A and B, and you want to look at entanglement of A with respect to B, you can imagine entanglement dynamics in a pictorial way, as represented in this picture here. Namely, you can imagine that at every point of this 1D system, you have pairs of quasi-particles that are being emitted with opposite momenta. So in some sort of light cone propagation. And these pairs of quasi-particles, for example, that are emitted in region A, eventually they will interact with some particle that was emitted in region B. And you could almost you could almost think of a process whereby you kind of count the crossings of these lines between A and B. And that counting would give you some sort of idea of the amount of entanglement that is accrued as time passes. And in fact, if you do that exercise, and this is relatively simple in context of CFT, what you find is this sort of structure that Calabrese and Cardy identified, namely that you would expect entanglement entropy for very large times to grow linearly with time. So to have some structure like this, some function times t, and this will happen until a certain time, because if the subsystem A is of finite length, there's a finite amount of growth that you can have. So this growth will happen up until some scale L over 2v, where v is some characteristic velocity in this quantum system. And then after that, you're gonna have another behavior, which is saturation. So your entanglement will saturate to some value, which depends on the length of subsystem A, is proportional to it. So these linear behaviors in time and in length are universal in this picture, but the curly A and curly B, the coefficients will be theory dependent. So they will depend on the parameters of your theory, on the type of quench that you did. Now this picture is very nice, very attractive because it's very simple and it's very intuitive, and it has been checked for many models. And so in my next slide, I'm going to show you some examples of things other people did where they see these behaviors. So one example that is quite nice is from this paper, Fagotti and Calabrese. I'm going to show you a picture that's directly from that paper. It doesn't really matter if you don't see all the captions, because what I want to show is essentially an example of the behavior I just described. By the way, this was done for a model which is integrable, and it's a discrete model, a lattice model is the XY chain. And here what they are doing is a quench of this magnetic field, this parameter H. So what you see in all these pictures is the von Neumann entropy, S of t, divided by the length of subsystem. And what you see in all cases, roughly, is you have a region where you have linear growth in time. Time is the horizontal axis, and then you have some sort of saturation. The separation between one regime and the other is not sharp, of course, because the formula I showed you before is just the leading asymptotic behavior. But in real physical systems, this transition is smooth, and there are corrections to these behaviors. And in fact, you see in many of these pictures, there are sort of oscillations on top of this kind of black line, if you wish, of this main behavior. But in essence, this model gives you a very good representation of how well that formula works, okay? However, what is interesting as well in integral models is that it seems this quasi-particle picture is not enough to describe all the behaviors that you can find for entanglement. And to illustrate that, I'm going to show you a picture from another recent paper. This is a paper by Kormus, Kolura, Takash, and Calabrese from 2016. And in this work, they looked at a quench for this Hamiltonian that you see in here. So this is an Ising chain with two fields, a longitudinal field and a vertical field. Longitudinal and, well, the two fields, HX and HZ. So you can do different quenches. You can quench one of the fields or the other, and depending what values you start from and how you quench. And again, ignore the legends in there, they're not so important. What is important is to see that in there you have the von Neumann entropy, and you see a variety of behaviors, a great variety of behaviors, in fact. So you see some of the plots show very clear linear growth, whereas in some of the plots, actually, you see no linear growth at all, almost. And you see lots of oscillations, and you see a strong suppression of growth, at least. Because these are numerical simulations, people can never conclude for sure there is no linear growth, because it might be that it just is so slow that you cannot see it for the times that you can access. So in this paper, what they said diplomatically is that linear growth is very strongly suppressed. And they identify also some sort of mechanism to explain why that might happen. They call this confinement. So what they said is that in this model, what you have is you can apply this quasi-particle picture, but not quite in the same way. So you're going to have this, you have a suppression of the line cone effect. So you have quasi-particles first propagating in a line cone, but then sort of interacting and coming back together and then separating again. So there is a sort of oscillation and suppression of entanglement due to the interaction in the system, because it's not a free system. So, so these are two good examples of this range of things that you can find. And what we did in the work that I'm going to present to you is to look at these problems from a quantum field theory perspective. So if you take these quantum spin chains and you take an appropriate scaling limit, you get some new theory, which is a QFT. And actually, in both cases, you get integrable QFTs. So there are two situations we looked at, one for each of the papers. In the first paper, we looked at the situation where hx is equals 0. And so in that case, if you fix hz equals 1, you have the critical Ising chain. So you have a chain that has a quantum critical point, which is a massless free fermion. If you take hz bigger than 1, you have the Ising field theory, which is a field theory with a mass scale, so it has a gap, and it's essentially a massive free fermion. Okay, it's still a free theory. So if that means that if you quench hz in this lattice in this situation, and you take the scaling limit, in effect, what you're doing is a mass quench in the Ising field theory. You're changing the mass of the fermion suddenly. So this is one situation where what is expected and what we see is linear growth of entanglement. On the other hand, if you fix hz equals 1, Okay, but now what you change is hx. What you have at the level of the lattice is a theory that is not integrable anymore, but the scaling limit of that theory is integrable, and it actually gives you a quantum field theory which is known by is called by experts the E8 minimal Toda field theory. So E8 minimal Toda field theory is integrable, so there is the usual properties, no particle production, and so on. And it is an interacting and rather complicated theory. It has 8 particles of different masses. Some of these particles can form bound states. So it is quite an interesting dynamics that happens in this theory. So, so these are the 2 QFTs that we looked at. So 2 continuum limits of this particular chain and 2 types of quenches. And essentially we found 2 very different behaviors which correspond very much to what you see in these pictures here. So let me then start with the simplest case, which is easier to describe, and then I'll go to the more complicated one. So suppose you look at Ising field theory. So I just told you this is a theory which is essentially a massive free fermion. So initially we start with a theory that has a fermion of mass m0, and then we do a quench at time 0, and we go from this mass m0 to some mass m. And we ask ourselves what is going to happen to entanglement. So just to give you an idea of what the scaling limit means, so we are again in that situation I just described, and there is a relationship, of course, between the parameters in this chain and the parameters in the field theory. And for this theory, it's quite simple. So essentially, the mass of the particle goes with 1 minus the magnetic field. And then you also have a relationship between the velocity, the lattice spacing, which is A, and the coupling in the chain. And in the scaling limit, you're taking A to 0, J to infinity simultaneously in some controlled way, while you keep your field Hz rather close to 1. So this is the universal region where you have QFT. Here's a picture from our second paper that illustrates that. So essentially, we are now moving along this horizontal line, starting from Hz1 and going to Hz, so taking some Hz bigger than 1 and quenching that value. So what should we expect to find? Well, one thing I should clarify is that what we looked at in our 2 papers, in fact, is a situation that's a tiny bit different from the one I showed you earlier. So earlier I was talking about 2 complementary regions. We're still looking at that, but just for simplicity, in our case, it's simpler to look at 2 semi-infinite regions. So our region A is not going to be finite in length, but it's going to be both regions infinitely large. The only difference this makes to the picture of Cardi and Calabrese is that there is no saturation expected. So if both regions are infinitely large, what you would expect is that the entanglement increases linearly with time for all times. And this is indeed what we find analytically and also numerically. Now, for this theory, there's a lot that we know about what we should expect. The first thing is that at the lattice level, this is already very well understood. And actually in this paper here, they found the precise exact formulae for those coefficients curly A and curly B that you saw in my formula at the beginning. So the coefficient of the linear growth of time and the coefficient of the linear saturation. These are known precisely. So we can actually, if you do a QFT calculation, or a lattice calculation, you can take the continuous limit and compare to the results from QFT. And we found that they agree. There is also the results for other quantities for the same quench. So there is also, people have also studied the magnetization in the Ising chain for this particular quench. So people also know how magnetization behaves. So there is a lot that is known for this situation, but people hadn't computed it starting from the QFT. This had not been done. So, so before I show you the result, the main result, I'll give you just some basic definitions so you know precisely what we are computing and how. So I talk about von Neumann entropy. In fact, in most of the work that we did, we looked at Renyi entropies instead. And Renyi entropies, they are defined, as you see here in this formula. So they depend on some index n. So this will be the nth Renyi entropy. And inside the log, you have a very common object, which is the trace of rho to the n, where rho is the reduced density matrix for the subsystem A I was showing you earlier. Now, the limit when n goes to 1 of these Renyi entropies gives you the von Neumann entropy. So all these quantities are related, but the approach that we use in QFT is particularly suited to compute Renyi entropies for integer indices. So that's why we looked at those first. Now, the reduced density matrix for this particular problem of the Ising mass quench formally at least, it would look like something like this. So you have some ground state, 0, you start from, and then what you're doing is you are evolving this state with a Hamiltonian, which depends on a new mass scale. So remember, we went from some mass m0 to some mass m. So this is generally the definition of a quantum quench or a quench. So you start with an eigenstate of some Hamiltonian and you evolve with a different Hamiltonian. So numerically, you would need to compute that matrix and diagonalize it. In the Ising, in this particular case, actually this can be done by exact diagonalization because this is a free theory. So I already said this. This is the Hamiltonian. Now, in quantum field theory, there is a particular way of computing measures of entanglement, which is based on using a type of local field, which is called a branch point twist field. And this is an approach I've worked a lot on since 2008. In fact, we started working on this. So I'll just give you the rough idea of what this is. The idea is simply that in quantum field theory, quantities such as this trace of rho n in particular, there's a picture in which they can be expressed as correlation functions of some field. And that field is called a branch point twist field. The idea that there was a connection between the trace of rho to the end and some correlation function actually first appeared in the paper of Calabrese-Cardia about entanglement that everybody knows about, the famous logarithmic scaling of entanglement. However, later on, we took that idea and we refined it a little bit. We extended it to massive theories. I mean, they were talking about CFT, and we gave an interpretation to that field as a symmetry field. Why is that? Because when you talk about branch point twist fields, you have to talk also about a replica theory. So essentially, you have to imagine that you now have n copies of your model, whatever it was. In this case, it's Ising field theory. So you take an integer number of copies, n, the same n as in the Renyi entropy. And what you have now is, well, a new theory which has in particular cyclic permutation symmetry between those copies. And because you have all this symmetry in there, you have essentially a local field associated to that symmetry. And the local field associated to cyclic permutation symmetry is this branch point twist field that we studied in this paper I showed you there. Now, the interesting thing is that in terms of this branch point twist field, this trace of rho to the n for the configuration I showed you is essentially a one-point function of this twist field. So the general idea is that if you want to compute actually any measure of entanglement with twist fields, you're going to need as many twist fields as boundary points between your regions. So because I took two semi-infinite regions, I only have one boundary point, and so I just need one field. And this is the reason why, for us, that is a simpler situation to look at than the situation of a finite region, where you would need two field insertions, a two-point function. So we are looking at a one-point function of this field I call T. So this is my twist field. And so essentially, if you compare this formula and that formula, the main difference is that this trace of rho to the n is replaced by the one-point function. And this is essentially what's happening. There is this
question.
See?
Yeah.
Sorry.
Yes. Maybe too elementary, but you can use you can use a replica trick in any situation to calculate an entropy of this kind. What's the simplification that, in the field theoretic case makes it makes it just an expectation value of this other field? So something simplified in the sense that if I use it in a replicated lattice problem, it's very cumbersome.
What makes it okay? I don't know if I understand exactly the question. So I mean, I guess, well, the main motivation is that in integral quantum field theory especially, there's a lot of techniques people have developed to compute correlation functions. And so there's this whole technology that you have at your disposal to compute things exactly. And so if you can relate entanglement to any correlation function, that is usually an advantage, because then you can go and apply lots of techniques that you already knew about. Now, why this replica is involved, I mean, that has to do with the definition of this trace of rho to the n. So, I mean, there's this common picture in terms of, well, having n copies and having n manifolds that are connected to each other in a in a cyclic way, which is an expression of this trace. So the trace is cyclic. And this, so essentially you can map computation of entanglement entropy to a computation on a complicated manifold like this. The introduction of the twist field, what it allows you to do is to sort of remove all the structure of the manifold to go back to working on the complex plane, but with the insertion of this field that has some non-trivial properties with respect to other fields. So if you take other fields of the theory and you go around the twist field, the fields actually travel from one copy to the next and so on. So it implements this cyclical symmetry. I don't know if that helps clarify.
Okay,
things.
I think I get it.
Yeah.
Yeah, it does. Thanks.
Okay. So you have this 1-point function. This omega n represents this pre-quench ground state in the replica theory. So I put this index n to remind people that there is this replica idea. Then this epsilon in there is a UB cutoff. Usually in the work I do, we tend to write this epsilon in there just to indicate that in general, entanglement entropies will depend on some non-universal parameter. So this will be the equivalent of the lattice spacing if you are in the lattice. So there's going to be some non-universal corrections, but this epsilon is quite unimportant because in the end, we're going to always be looking at differences of entropies so that we can get rid of this epsilon. For example, typically we're going to be looking at entropy at T minus entropy at 0. And by subtracting the value at 0, immediately we subtract all this dependency on this UV cutoff. So this epsilon won't feature later on. It's not very important, but it's a sort of normalization. So this is what we are doing. Essentially, in our two papers, what we were doing is to compute this 1-point function for two different situations. All right. So let me, now that you know what we are doing, let me show you the main result for this Ising mass quench. So I'm going to just show you the result, and then I'll tell you a little bit about the method that we used to get it. But this is the final result, okay? So this is the result for the 1-point function, and actually normally we need to normalize by the norm of the state just to get something that makes sense. And this result is actually quite, well, if you know how it's computed, it's actually quite impressive in the sense that it takes a lot of work to get a formula like this. And in particular, the fact that we could show it is an exponential. It was quite non-trivial. So let me explain a little bit the different elements in that formula. So they're in blue. In the formula, you have two things in blue. These are constants, essentially. So a constant in the sense they don't depend on time. So this tau tilde is some vacuum expectation value of this field. Okay, so it's a constant, depends on the theory. And the A is also a constant, a function just of n. What is interesting, if you look at the formula, is that you will see some parameter in red, mu, that appears in several places. Now, you see that mu appears linearly here in this term, which is actually the only oscillatory term that you have in that formula. So you see that there are some oscillations that are actually suppressed by t to the 3/2. And these are linear with respect to this parameter. Now, this parameter mu is a parameter that is a measure of how big the quench is. So if you see the definition of mu, you see that if the masses are very close to each other, mu is very close to 0. So in a sense, if you write things in terms of mu, you are having a sort of perturbative expansion on the size of the quench. And this is interesting because what you quickly realize when you write this formula is that except for that oscillatory term, every other term is of order mu square, in fact. So this constant A in terms of mu is order mu square. This gamma here that goes in front of the term proportional to t is also of order mu square. Okay, and this term is already explicitly having mu squared. So in terms of the size of the quench, if you were looking just at the first order, you will only see oscillations, suppressed oscillations. You need to go to the next order to actually see the exponential decay and the other terms. Another interesting thing you'll notice is that if you remember from the previous page, the entanglement entropy is the logarithm of this, essentially. And so exponential decay in here is equivalent to linear growth of the entanglement. So when you take the log, get rid of the exponential, divide by 1 minus n, this gamma here is actually giving you the rate of growth of entanglement, of linear growth. And one interesting feature for this model is that this gamma here, this is exactly the same decay rate that people have found for the magnetization for this same quench. So what this is telling us is that in a way the behavior of the entanglement is not a separate behavior from the behaviors of other local observables. If you have a magnetization that is decaying exponentially, actually the 1-point function of twist field is also decaying exponentially almost with the same rate, except for this n and this 2. And so these behaviors are part of a more general behavior in the theory. And exponential decay for the entanglement entropy is equivalent to linear growth, in fact, if you then take the log of this 1-point function. So, as I said, for small quenches, you would only see oscillations. And perhaps just to mention it without showing it, mathematically, actually, the most impressive result was to be able to prove that all these terms really do exponentiate. And what I mean by this is that the computation of this 1-point function is a sort of perturbative process. So you get this as an expansion with many terms. And when you do the calculation, actually what you initially get is not this exponential, you actually get 1 plus the exponent plus further terms. So you get the expansion of the exponential. You only realize that this whole thing exponentiates when you look at the more deep structure of those terms in that expansion. And that structure is particularly simple because this theory is free. And that was the reason, that's why we were actually eventually able to prove that we had really an exponential of all those terms. So this is something we proved fully in the second paper I mentioned before. It's a technical detail, but it's a rather non-trivial for QFT. So we have all these behaviors in there. So linear growth and oscillations, exactly as you were seeing in the first picture I showed at the beginning when I was giving you examples of the linear growth in spin chains. Let me just show you some numerical results just to convince you that this really matches the numerical simulation. So numerically, what we do is, well, we are doing an exact analyzation of this Ising spin chain and taking a scaling limit. One thing that actually is interesting to check is that when we do the numerical simulation, we can only look really at a finite interval of the Ising spin chain. So in numerics, we cannot have two semi-infinite intervals. So numerically, what we are computing really is a 2-point function of twist fields. We can, of course, take the length to be sufficiently long, sufficiently large, so that hopefully we recover our analytic result. But then what we should observe is this property of clustering. So what we want to see is that this 2-point function we compute numerically in the limit of L large becomes our 1-point function squared. And this is something we were able to check by effectively seeing that there's very good agreement between the numerics and the analytic formula. So there is clustering even for this out of equilibrium situation, which is something that is not completely trivial, even if it was expected. Now, the two pictures that you have in there, just to check, you still hearing me, everyone?
Yes,
Yeah,
please.
okay,
Yep.
because I stopped seeing you, so I didn't know. Okay, great. So just to explain a little bit, in this picture, so this is for a quench from a mass of 0.048 to 0.04. So the size of the quench is rather small here. And we are looking at the second and the third Renyi entropy in these two pictures. And you see that there is, if you look at the labels, there is a subtraction. So we are looking at entropy at time t minus entropy at time 0 in both cases for N2 and for N3. And there are lots of things in the legend you won't understand because I didn't define those functions. But let me just explain. So the black dots, this is the numerical results from exact diagonalization. And then the other curves that you see here are the results that you get from including more and more terms in this analytic exponential formula. So if, for example, if you only include the oscillatory term, okay, that would be what I call C2 here. So the term that gives you damp oscillations, then what you would see is this curve in here. So you see that the oscillatory term is very much there and it's of first order in the size of the quench, but it's certainly not enough to give you a very good approximation of the numerical results. So you need to go to order mu squared to get something more accurate. If you add the linear term, so the exponential decay in time or linear growth in time, then you start to get something that is much more accurate. And then this C4 plus R, these are terms of order 1 over T, 1 over TQ. So these are higher order corrections that makes the approximation even better. And finally, if you put the constant a in, there was also a constant in the exponent, that actually allows you to bring these analytic curves a little bit down so that they match the numerical results very perfectly. So even this constant a has an important role to play. So in summary, the agreement is very, very good. So this is nice. It all works, and okay, that's all very good. So let me now tell you a little bit about how we did this calculation. I'm just going to mention the names of the methods and not tell you very much about them because they're very technical. But okay.
Sorry, what was the right plot?
So right and left, this is Renyi 2, Renyi 3. So these are two Renyi entropies, index 2, index 3. So they're very similar. That's why you have divided by 2 in some of these things, because it's divided by 1 minus n. So actually, this is 3, so it should be a 2 there. So I don't know, it's some normalization. But these 2 that you see there is the 1 minus n, the 1 minus 3. So
and
what? Are very, very
sorry.
similar.
What happens for larger quenches?
Well, so actually, did we explore this very much in here? It's been a while we did this paper, so we. I mean, I don't think we explored larger quenches very much for this work, but for the other situation that I'm going to describe a bit later, we looked at quenches. So in there, we explored that a bit more. I think here we stayed sort of on a small medium. Even this one here is not, I mean, it's small, but it's not so small. So I don't know. Actually, I don't remember if we looked at that, but it wasn't our focus actually to look at very large quenches. So I cannot tell you when this fails, but I suppose that at some point it won't be very good. It won't be as good because higher order corrections in time will start to play a role. That's the expectation.
Thank you.
Yeah. Okay. So let me tell you a little bit about the technique. So as I already said many times, we need to compute this 1-point function of this twist field. So in QFT, we are lucky that we have quite a few techniques, especially in integral QFT, to compute these correlation functions. And in the out of equilibrium situation, in fact, there are mainly 2 techniques that we were familiar with, where people have computed 1-point functions of some field after a global quench. So I'm going to tell you a little bit about each of them, and I'm going to give you some positives and some negatives about each technique. So both techniques are actually perturbative, but they are perturbative on different things. So the first one is a technique that was proposed by Aldo Delfino in 2014. This is called, I call it perturbation theory around the pre-quench state. And this is a theory that is really based on, so the perturbative parameter here is the size of the quench. So it would be the mu in my previous formula, if you still remember what that was, the 1 minus m over m0. So you need that to be small to apply this kind of perturbation theory. And once you make that small, then it is a very standard kind of type of perturbation theory. The good thing about this approach is that it's applicable to any global quench. So as long as you have a theory, you know what the action of the Lagrangian is, and you have a parameter there, a coupling that you are changing the whole theory, then you can go and apply this approach. So that is nice. The bad thing is, of course, you need the quench to be small, so it doesn't let you look at very large quenches. It's only been developed at first order in addition. So although this should work for all orders in perturbation theory, the fact is that if you want to go to higher orders, there are singularities that emerge in the perturbation theory. And so far as I know, nobody has managed to resolve that successfully. So we can only get first order results from this technique. And so it will only capture first order features for small quenches. And this is this is quite a big negative if you think about the model I just talked about. So if you remember the result for the Ising max quench, we just showed that if you actually want to see the most relevant features, which is the linear growth, you need to go to second order on the size of the quench. And so this method would miss all of those terms. It would just give us the damp oscillations, which don't really match the exact result very well. It's just part of it. So this is one thing that we can do nonetheless. There is another type of perturbation theory, which is actually a large time perturbative expansion. which is based on using form factors. I'll say a bit more about that in a minute, of the post-quench theory. And this is a technique that is actually the technique we use to prove this exponential result. And this was particularly developed by Schurich and Esler in a paper they wrote in 2012, where they looked at the magnetization in the Ising field theory for exactly this quench. So actually they did a calculation that is very, very similar to what we did. We were very much inspired by their work. And they found a very similar exponential formula for the 1-point function for the magnetization in the Ising theory. So they actually found a formula that has exactly the same kinds of terms, exponential decay in time, an oscillatory part, a 1/t. They found pretty much exactly the same. They just didn't manage to prove that the whole thing exponentiates, but I mean, they were, they got a very similar result and very similar structure. So this technique is quite nice for various reasons. It has sort of one defect, which is relatively big, which is that it requires a particular relationship between the pre-quench and the post-quench states of the theory. So the pre-quench state must have a very particular structure, which is called the structure of a squeezed coherent state. So there must be a way to express the pre-quench ground state in terms of states of the post-quench theory. And of course, that expression is not always available and is only known for a few theories. So this is a big limitation, but it is very well known for this particular example we studied. Apart from that, there is no restriction on the size of the quench. It's based on a form factor expansion, so an expansion on matrix elements of this twist field on post-quench states. And if you know those matrix elements, it means you can develop this at any order, in time and in the quench parameter. In the particular case of Ising and of Schurich and Esler, there is a technique they used, which they call kappa regularization. And this is a technical aspect of the calculation. But what it means is that when you do this form factor expansion, there are usually singularities that appear that you have to deal with in some way. And well, Esler and Koenig, they came up with a very simple way to do that, which essentially means that you shift the poles by some kappa, you do the calculation, and then at the end take kappa to 0. Now, for the Ising model, this works perfectly, but there are some doubts that this really captures everything for interacting theories. So there are some questions about whether one should keep using this technique if you want to treat more complicated cases. But what is good about it is that it's simple. And so this technique will capture high order features for small quenches. Okay, so as I said, this is what we really use to get that final formula I showed you. So, okay, so these are the two ways we can do things. Let me tell you a little bit about this squeezed coherent state that I mentioned here, just to give you a flavor of what we are computing. So this idea of this squeezed coherent states is this. So there are some papers, well, more recent ones by Musard and collaborators, where they gave a formula for this relationship between the pre-quench ground state and the post-quench ground state. And it turns out that for some quenches and for some theories, especially free theories, you can find an exact relationship between them for this type of quench. And the relationship looks like this. So there is an exponential, you have the creation operators on the Ising field theory, and then you have this function k in here, which will be characteristic of this quench and which depends on these two masses before and after the quench. So they were able to compute that function, and that's why for this quench we can compute everything. Now, as you can imagine, if you know that expression, if you know that state, then in principle you can compute any 1-point function. You just place your local field, you sandwich it between the state, and then you expand the state. And when you expand the state, you get matrix elements of the field. In our case, it will be the twist field. This coherent state is quite nice because it's actually really an analytic expression of this quasi-particle picture of Calabrese and Cardy. If you look at that state, what it's telling you is that you always have particles produced in pairs with opposite momenta. This is what the state is expressing. So whenever this quasi-particle picture holds, it is expected there will be a state representation like this. If you are doing twist fields, there's a very small change to this picture. The only thing that changes is that now you have n copies. So you're going to have n types of creation operators in here. And so you will have a sum, and your state will have a dependency on n, but the function k is the same, everything else is the same. So it's just a bit more complicated. And so you can compute this in the same fashion. You get an expansion in matrix elements, both of numerator and, well, in the numerator, the denominator also has its own expansion. So in effect, you get an expansion in powers of this function k in there. So in this case, you can think that the perturbative, well, the perturbation theory is almost, you can almost say it's in k. I mean, it's a bit of an abuse of language because there are integrals involved and so on. But in essence, every time you expand this exponential, you get terms that have a k squared, and so on. So this is all very similar to the structure of monetization, as I told you. And in particular, for the Ising mass quench again, if you just look at terms that have order k, only one of these k matrices, you actually get the leading oscillations of entanglement. So this term that was proportional to mu, to the size of the quench. And if you compute all terms of order k squared as well, you get the rest of the features I show you. So you get the linear growth, the constant correction, and other subleading oscillations, the term of that goes like 1 over t, everything. And this is actually what we did. So we computed these two first orders, and then later on we look at the structure of this function, and we realized that not only these were the first orders, but that this whole structure could be exponentiated. Okay, so this concludes the part about the Ising mass quench. So let me tell you a bit now at in the last part of my talk about the second paper I mentioned, which is a letter where we looked at a different quench, the one of the E8 Toda field theory. So now we know the main techniques that we can use. So let's look at this other case and see what happens. So what is this case? Well, so again, we go back to our lattice model. So we have this Hamiltonian. We fix hz equals 1, and hx it has a finite value, and we're going to quench this hx. From the point of view of the quantum field theory, quenching hx is equivalent to changing some mass scale as well, just like in Ising field theory. But in this case, the relationship between the mass and the field here is a bit confusing because we use, somehow in the QFT, we use a name for the coupling, which is lambda, but this lambda is proportional to this h. So you can think of them as being the same thing as in this picture here. So if you quench h, you are quenching lambda, and if you quench lambda, you change this mass scale that scales with the field in this non-trivial way in this particular theory. Now, I told you earlier that this E8 Toda field theory has 8 particles. So there isn't just a single mass scale, it seems. But in fact, there is, because actually all the masses in this theory, they are all proportional to the mass of the lightest particle. So you can think of this mass here as the mass of the lightest particle. All the others are proportional to this, and the mass ratios are constant in this theory, are fixed. Okay. So if you divide any mass of any other particle by this mass m0, you get some value that is known, something like cosine pi over 12, cosine pi over 4, some kind of analytic expressions like this. So if you change this mass scale, you're actually effectively changing all the masses in this E8 Toda field theory. So it's also mass quench, what you're doing. Now, it turns out that for this quench, the Zurich-Esler method, I've been advertising so much, cannot really be applied, and not yet at least. And I'll give you more details in my conclusion as to why we cannot use that. So the only thing that was available to us was to use this perturbation theory of Delfino and to do numerics and to compare both. I already emphasized that perturbation theory had limitations. We could only go at first order, so we could only look at small quenches. But nonetheless, this is the only method that was available to us, so we used it. What did we find? Well, we found some behavior which is very different from the Ising mass quench. So we found to be honest, for small quench and for relatively large times, we see actually no linear growth at all. Only if you look at very large times, you start to see some very slow growth. And what we saw also were persistent and undamped oscillations. On the Ising mass quench, there were oscillations, but they were damped because they depended on they were multiplied by 1 over t to the 3/2. But in this model, there's no 1 over t power. So you really have some cosine terms. You have some pure oscillations. And so Was this surprising? Well, it wasn't entirely surprising because as for the Ising mass quench, people have looked a lot at the monetization in this model as well, or the parameter. Sometimes they call it order parameter. For example, in these two papers, you will find a lot of analysis of that. And also for that parameter, they find very persistent oscillations. So again, there seems to be a connection between the two things. But what is surprising about our result is that it is very robust. So this is a case where we actually looked at large quenches, large tines, and these oscillations, they seem to be very persistent and not damped. And this was a bit of a surprise. So let me show you what is the formula that we play with, that we work with. So so this is the main analytic formula in that paper. It's a formula that you can get from this Delfino perturbation theory, so perturbation theory at first order. And so let me explain a little bit the terms in there. So this delta Sn, it represents the change of the Renyi entropy between time t and time 0. Okay, so difference. And what this tells us is that this model, this goes this is proportional to the size of the quench. So delta lambda here represents the change of this coupling lambda 2, which, remember, it was essentially the field Hx. Okay, so we have change of coupling divided by coupling. We have the 1/1 minus n, which is typical of Renyi entropies. Then we have this C sigma. This is a constant which is particular of E8 of the theory. It is known, so it has an analytic value. And then we have the sum of terms, and clearly, well, you see where the oscillations come from. So you have these cosines. These are A's, these are the scale masses. So these are essentially the masses of the A particles in this theory divided by the mass of the lightest particle, which after the quench is the mass M here. You have time, and then here you have this coefficient, which involves again the masses, and it involves some numbers which are the normalized one particle form factors. What does this mean? So these are matrix elements between so the vacuum of a field, between the vacuum and a one particle state, a one particle excitation. And it turns out that for this theory, these one particle form factors are not zero. Actually, for the Ising field theory I described earlier, they are zero. And that's why these kind of terms do not appear in our formula. But for this EA theory, they are there, they are non-vanishing. And here you have the ones of the twist field, so the T, and you have the ones of a field sigma, which is kind of the order parameter. It's another local field of this theory that gets involved in the expansion. Then there is some constant, which is not so important. These are the conformal dimensions of the fields. They appear there essentially because of the way the vacuum expectation value of twist field scales. So it's essentially dimensional analysis why these appear here. These are some numbers. Then there are some other terms. So this is not even the full contribution of the first order perturbation theory. There will be terms with two particle form factors, higher particle form factors, but these are very much smaller. They are expected to be, at least. And then, of course, you would still have second order contributions and, well, the full expansion. So this is, in a way, a very small part of a very long series, but interestingly, seems to describe what happens very well already. So here's a picture of some comparison between numerics and this formula. The numerics, in this case, they are done with, actually, I'll written later, with a method, which is the ITEBD method that uses matrix product states at its core. And what you see here in this picture is sort of vertically, you have two different quenches. So here is delta Hx over Hx minus 0.04 and plus 0.05. So two small quenches, relatively small. And what we have here is on the horizontal first line is the von Neumann entropy. And on the second line is the Renyi 2, second Renyi entropy, just to see. And the dots are numerical, and the curve is this formula, essentially, that you're seeing. Now, the match is very, very good. You might ask, are there some fitting parameters, some adjustments that you need to make? Yes, there is only one adjustment, which is that the numerical results have to be shifted a little bit up or down. And this is because there are, in particular, all these order 2 terms, for example, or the second order terms that we are not taking into account, among which there are some constant contributions. And so the numerical results, they differ from this analytic formula by some shift, which is rather small. We gave the values precisely in our paper. But once you add that shift accordingly, everything else is really a match with the formula. So it's still a very good agreement. The times that we go to here, they're actually much bigger than the ones I showed you for Ising field theory in the other pictures. But even after 30 time intervals, you see that there is actually no trace of any linear growth. The oscillatory part, the formula just with oscillation seems too much to describe the result very well. One thing that you can do as well is to take the Fourier transform of these numerical results. And when you do that, you can identify very well the frequencies of the oscillations that are involved. And also, in fact, you can do an indirect measurement of these coefficients here. And this is done, as I told you, with this method of ITEBD. This was done by my collaborator, Matej Lenches. So here you see these two pictures in black and red. These are, again, the two quenches, the same two quenches we consider here, minus 0.04 and 0.05. And so what you see here, so you see a number of peaks. So these peaks you can associate with the frequencies that contribute. And you see that, well, the largest one, you have it for the lightest particle. Here I call it M1. Sorry, it's not fully consistent. Here I call it M. So it's the same mass scale. So this is the lightest particle, and you see the big peak in there. And then for the next one, you have M2 here. And then you're going to have, I think you have M3 somewhere. Yeah, this is M3, which for this theory is very close to M1. So they're almost together. And then this is M4. So the peaks corresponding to the first four lightest particles are rather clear from the Fourier transform. Then you get some other peaks which correspond to combinations of masses. The reason for that is that in this particular theory, the masses of the particles 5, 6, 7, and 8, they're actually, so M5 is actually bigger than twice M1 already, and it's bigger than M1 plus M2. So in a sense, the contributions of some of the dot terms here, they sort of are more relevant, more visible than the contributions of some of the terms included in this sum for the heavier particles, if you wish. And that's why you see, for example, M1 plus M2 resonance appearing here very clearly, and you don't see M5. Okay, so you see the first four very clearly. The horizontal lines in here that we drew by hand, so these are predicted from this formula. So these have to do with the coefficients of these cosines. So the height of the peaks has something to do with these coefficients. And you see that they are predicted very accurately. So for M2, you see that it's meeting it very well. For M3, it's also pretty good. And for M4, it's also pretty good. So this numerical approach not only is showing us that the scaling limit works and it matches the QFT prediction, but the Fourier transform gives us a sort of measurement of the one particle form factors in some way of these coefficients and the mass ratios. Okay, so identifies the frequencies and the coefficients of these oscillatory terms. Okay, so what can we say about this result? So the agreement with numerics for small quenches and short times is quite remarkable, but it's expected from perturbation theory. So if perturbation theory is any good, this is the regime in which it should work, and it seems to work. Now, what is a bit surprising is that we were able to see that these undamped oscillations persist for large times and quenches. We hadn't actually analyzed that very much when we first submitted our preprint, but then there were lots of people writing to us, sort of telling us that surely these oscillations were going to be damped if we went to large enough times. They couldn't quite believe these oscillations were so robust. So we did a bit more numerics, and this is what we got. So here we have the von Neumann entropy. Again, we're looking at a very large quench. So the ratio here is 1. So it's a quench of 100%. So we have some field and we double it. We're looking at times that in the previous picture, they were going up to 30. Here we go up to 900. So it's quite a few time periods. And what do we see? Well, we see a slight growth. So there is some growth. I mean, the picture is not enough to tell us if it's linear or not, but there is some quite suppressed growth that is there. But if you look at oscillations, they're very robust. They don't seem to be damped at all. There's actually even some bigger oscillation we can identify, which turns out to be related to twice the mass of particle 1 minus the mass of particle 3. So you get all these contributions from combinations of the masses. So we knew that first order perturbation theory can miss the linear growth of entanglement, and that seems to be what happens here. So we see that happening numerically. But there is some expectation from people that are experts in these form factor expansions that if you could do perturbation theory at higher orders, there should be some corrections to the oscillation frequencies, and there should also be some damping eventually. So there is some idea that if you resum terms, eventually this oscillatory part, these cosines, they will get multiplied by an exponentially decaying contribution. And so there will be damping eventually. So, I mean, we cannot conclusively say it will never happen because we cannot go to infinite times, but for quite large times, it is not there. So this is something that appears rather unique for this model and still needs to be understood better. So let me tell you a little bit more about the general conclusion and a bit more explanation of results. So I hope the talk gave you some idea that how this branch point twist field approach can be useful also in out of equilibrium situations. It gives us analytic and quantitative features of entanglement dynamics and qualitative features as well. This twist field treatment gives us actually analytic evidence that the dynamics of entanglement and the dynamics of other local field averages are analogous. So I said many times that there seems to be very many similarities between the behavior of this one-point function of twist field and one-point function of magnetization in many, many theories. And in fact, this is an idea that has been explored further recently in this paper that I mentioned here. So in a sense, the behavior of entanglement is just one more behavior of one more local field in a theory after a quench. So this approach, if we can develop it further, gives us the potential maybe to show precisely whether or not there is linear growth in some system in cases where the numerical techniques do not allow us to access sufficiently large times. So that could be an application. We are not there yet. I'll tell you why in a minute, but this is an ambition that we have. Ultimately, maybe we will be able to classify models, states, and quenches by some universal features of entanglement, such as linear growth, or absence of linear growth, persistent oscillations or not. For now, what we can at least say is that the linear growth of entanglement, the suppression of that, and the presence of persistent oscillations they don't seem to be just associated with integrability and breaking of integrability, which I think was an idea that existed previous to this work, that somehow it was the presence of interaction or the breaking of integrability that was causing things to be so different. This might be a bit controversial because it is true that the second model I discussed from the point of view of the spin chain model is non-integrable, but the QFT version is integrable, okay? And also from other techniques that people use, such as, for example, hydrodynamic, so GHD, generalized hydrodynamics, which is a technique I'm also a bit familiar with. What people tend to find is that features of integrability are very robust. So even if you try to break integrability, if you look at correlators, for a very long time, they're going to still behave as if the theory was integrable. So in a sense, this second model with this spin chain that is non-integrable is not that far from integrability. So so we think integrability is not really the key feature here explaining these behaviors. I told you quite a few times that the approach of Schurich and Essler seemed to be a little bit superior than the perturbation theory of Delfino, simply because you didn't have to have a small quench and you could predict higher order terms, in particular linear growth in the mass quench. So you might ask, why didn't we use this for the EA theory as well, if it gives you more? The reason is that we couldn't yet. And well, one reason is that if you want to use that technique, you need this coherent state. For the EA theory, we don't have a full knowledge of this coherent state expression. We have some partial knowledge. So there are some papers where people have tried to estimate these functions K that are going to appear in this coherent state formula. And for EA, there are going to be 8 of them because there are 8 different particles. So there are some estimates of these functions that are based on computing overlaps between states in the pre-quench and post-quench theory. So a little bit is known, but not as much as for the simpler quench I described at the beginning. From what is known, actually, it is actually not surprising that linear growth should be very suppressed in this model. And the reason is that in this paper I just cite here, people looked at these functions K and they found that their order of magnitude is approximately 1 order of magnitude smaller than for the Ising mass quench at their maximum. Okay, why does that matter? Because actually the rate of growth, of linear growth of entanglement, which was this parameter gamma in the Ising mass quench, it goes essentially like k squared. So it means that for E8, it's kind of expected to be 2 orders of magnitude smaller than for the Ising mass quench. And this is compatible with what we see numerically. So that is not so surprising. There is another limitation, which is this kappa regularization. I told you that we are not sure that this is complete or will work, will not miss some terms for interacting theories. There is some evidence that this can happen. And what that means is that if we want to do things really correctly, we should have a better way to regularize these form factor expansions. And usually the way that is considered rigorous in our area is to do some finite volume regularization. And this is complicated to do. And for the twist field, it hasn't been done yet. So this is a big open problem we should look into. So within this approach, we need to develop a good regularization scheme that we can trust. And then ideally, we should look at some model, some integral model that is interacting, and look for first and second order terms in the quench parameter, and hopefully see if those, hopefully those would encapsulate, based on existing evidence, those will give us the leading behaviors of entanglement, and it will allow us to draw some conclusions as to whether linear growth is there or is not there, and for which theories. So with that, I conclude, and thanks a lot for your attention.
Great, thank you very much for this nice talk. So we ran a bit over time, so I'm going to stop the recording. That's fine. I'm just going to stop the recording now, and then we can have informal discussion.
Yep, good.